Hello everyone. In this times, I'd like to introduce the reliability approach on the internal erosion risk assessment of earth dam and the tailing dam. Hi, my name is Sang Ho. I'm working as a testing supervisor at the water district in the San Francisco Bay Area. My presentation time is limited to 25 minutes, so if you need any question during my presentation, please put down the slide page number and give me your question after my presentation. And I appreciate your understanding. So what is the internal erosion and its consequences? So what is the internal erosion process? So internal erosion is another name of the piping. This is a more official and academic title. The piping is starting from the suffusion, which describes the fine particle migration within the porous media in micro scale. And piping can be considered as a continuous development of suffusion in the macro scale. So always the size is scaled up as the migration starting from the downstream to the upstream. Piping is not necessarily limited within the dam structure. It's also feasible at the underlying the alluvial soil strata below dams. And even piping started from the micro scale, but if the problem is left unattended, the consequence is not ignorable. As you can see, it eventually makes a serious damage on the dam structure, even also cause the total dam structure failure. And piping problem also feasible underlying the alluvial soil strata. So that piping problem eventually caused that significant impact on the stability of the dams. So if you find some puddle or boiling situation at the toe area of a dam, you should take an immediate investigation over the piping process. So what material properties impact on the internal erosions? So piping starting from the suffusion, and suffusion, so we called another name is the self-segregation process. And those processes relate to the particle size distribution and the relative density of the site soil. And from those two input parameters, you can calculate the constriction size and the maximum conduit size, other words, piping flow channel size. And from the comparison, those two erodible particle size and the conduit size, and you can eventually calculate that how much particle is remained and how much fine particle is eroded out after piping process. So I'm going to explain the definition of a constriction size and the maximum conduit size in the later slide. In 1985, the Kenney law suggests the design criteria, so how to estimate the internal soil stability. They proposed that criteria H equaled 1.3 times F, and this H is defined as a difference of a fraction corresponding to 4 times D and the diameter D. As you can see, the green and the orange gradation curve, that relationship can be plotted in the FH diagram, and those relationship F and H is consistently above that 1.3 times F criteria presented in the red line. However, you can see the blue gradation curve is better the graded grain size distribution. That relationship F and H is for below of the criteria at a fraction above 50%. So those and blue gradation curve is we can call is internally unstable soil. And Kenney Load, they proposed this criteria based on their laboratory test on the many non-cohesive type soil gradation. And from right-hand right-hand side graph and FH diagram result consistently shows that relationship is always above those 1.3 times F criteria. However, the internally unstable soil is a pore below that criteria, and so I want to make a note. Their test is always performed under the densely compacted condition. So we need to figure out and the methodology how to evaluate the internal stability for the loosely packed condition. Relative density is another important parameter to be considered in the piping risk assessment. When you build the embankment dam on the rock, the abutment side area, the new embankment will start the settlement from that lower portion of the dam due to the over self-weight. But the crest zone, the dam area will sustain by the supporting from the breaching impact from the abutment rock slope. So what happens in middle zone if the top portion is sustained but lower portion is settled down? So the middle portion will susceptible of a piping flow channel generation because of the relative density is decreased. So how to quantify the internal erosion risk? The constriction as defined is a two-dimensional area concept. So when you consider this sphere is a packing structure of a soil and individual soil particle producing the inner space and also the flow channels between those particles. So the constriction is related to the flow channel and through those the pore structure. So constriction is two-dimensional area concept size, area flow channel size, and pore space is considered as a inner space in the three-dimensional the space concept. So how to derive the constriction size distribution from the soil particle size distribution? The first step is you need to evaluate the effective particle size distribution, which is closely related to describe constriction size of the pore structure. And you need to take an integral of 1 over x. X is the particle size, and powered by the beta. Exponent beta value is range from the 0 to 3. So beta equals 0 means the mass-based particle size distribution, and beta equals 3 means number-based particle size distribution. A Swedish researcher, he investigated through the laboratory test and finding out the closest beta value described that the constriction structure of the pore. So from his study, and he concluded that beta is close to 1. There's some different types of a gradation curve, particle size distribution curve, presenting the internal stability. This blue line is presenting internally stable, and this red line is internally unstable, and this green line is a gap graded type particle size distribution. And this green dot, red dot, the line is presenting the constriction size curve derived from the particle size distribution in the solid line. The red line is presenting the densely compacted condition, and this green line is presenting the loosely packed condition. So as you can see, the densely compacted condition produced more smaller construction size compared to the loosely packed condition. And you can see that from the internally stable soil, the construction size curve is produced a little separated from that original particle size distribution curve. However, internally unstable and gap-graded soil produce the construction curve is much closer to original particle size distribution. And for the passing probability analysis, so you can estimate that piping flow channel size. If you have these types of a solid line particle size distribution curve, and you can derive of a constriction size depends on the relative density, and so you can estimate from the construction size curve the matching 20%, 28% of corresponding the construction size that will produce the piping flow channel size. Particles smaller than this piping channel size will be eroded out, and the coarse particle greater than this piping flow channel will be remained. So those two, the solid line, the black dot, the solid line is presenting a regradation of the particle size after piping process. In respect, each case is corresponding to densely compacted and the loosely packed condition. So the loose packed condition definitely shows a much larger fine particle migrations happen after piping process. We can call the suffusion in the micro scale as a piping, because a piping is a continuous process development, enlarged in size and also developed from the downstream to the upstream. So we should investigate so this fine particle migration is successfully progressed as that analysis domains is increased. So this even the suffusion started from the micro scale in the pore structure unit, but depends on that accessible construction locations, and it determined whether this fine particle migration is successful or it will stop. So from the renormalization technique, we can evaluate that the piping continuation probability. So bottom line, actually we need to find out scale invariant defect of the pore structure to associate it the piping development. So from that study, actually we can evaluate that the critical piping flow channel size is corresponding to 20% of a cumulative construction size. So from now, I'm going to briefly show that the program from this probability model, we can estimate construction size and compare to that construction size to the original particle size curve, how we can calculate that the fine particle mass fraction eroded out from the piping process. The first example is I'm going to introduce you. This program, it has two input section is for the base soil grain size distribution, and the second the input section is for the sieve size. So sieve actually has the percentage opening area and also its opening size itself. So first thing is just to make the 0. That means your sieve is closed. That is you just examine the self-segregation process. Okay, so no actually fine particle it's allowed to pass through that sieve. So you can see that you maybe whatever you can erase that, and you just plug in those any number, and depends on the passing curve, and you can generate, and then you get this curve, and you eventually getting the constriction size distribution also from the calculation. So as I mentioned before, now is the first case is the sieve is closed and the opening is closed, and then you can calculate. You get times with this eventual the accumulation of fine is you can observe it. But the lab floor actually model, and you can actually a different opening size applied, right? And then you applied also the different these types of soil types, and the unstable and the stable and the gap grade types. So you can also, you maybe just to erase everything, and then you just generated, plug in those the number, and then you create it. This is automatically and changed generated that the grain size curve, the original, and then you apply now is just opening size here, the first M42. Okay, now is you apply this number, and you just change also relative density. If the 0.2 is very loose, maybe 0.9 is actually very dense. So first thing is you just loose apply 0.2, and you can calculate, and you will get that this type is all, the fine particle is all pass through to that. So it doesn't reach that kind of some breaching formation. If we maybe just increase at 0.9, it's a relative density. Let's see, so how is it different apply? And you will get that, or maybe it's by a chance, it's a kind of the fine particle is a kind of it's less reduced and sustained, and on the so one is a kind of it's an interface zone, and the second is actually the upper soil upstream area. So you can see kind of it's a progression here. Let's just erase again and do calculation. Yeah, it's the same conclusion. Okay, so you're eventually getting these types of the measurement is a weight fraction of each sub layer. So what percentage of 25% is the soil is eroded at the first layer, and actually close to the original point is just 4% is the X migration. So what is the reliability analysis, and how to evaluate the internal erosion risk? As many of you already know, the LRFD, load resistance factor design, the methodology compared that the data distribution of load and resistance, not comparing two deterministic value. So as you can see that the data distribution represented by the mean and variance, and you compare those two data distribution, load and resistance, you can calculate that overlap this gray area as the probability of failure. If you apply the same scheme to the piping problem, and the resistance side is we can compare the erodible particle size distribution, and the load side is we can compare to the piping flow channel size. So piping flow channel size is greater than erodible particle size, or particle size is smaller than the piping flow channels, that will produce the piping problem, right? So that overlap the gray area will the probability of failure at the piping the risk. As we already know, the well-grade type soil is more susceptible to piping the problem. The well-grade type soil usually shows the wide range of the piping flow channel size, and also the erodible particle size distribution. So those wide range of data distribution is increase that overlap area in the probability of failure compared to the narrow variation of the piping flow channel and the erodible particle size. The poorly graded soil also produced some piping problem if that graded soil is poorly loosely packed. So those loosely packed condition, the piping flow channel size will shift to the right-hand side, to the erodible particle size. So those created some that overlap the probability of failure. So from now on, I'm gonna briefly introduce the case study, to how to use that the probability method, to how to evaluate that the piping risk from the site investigation field data. So I took the example from the FEMA manual, and embankment dam is built on that two alluvial soil 1 and soil 2. You can assume the three different piping flow channel paths. The path A directly through that dam structure, and path B is through the alluvial soil 1, and path C is follow that alluvial soil 2. So we're gonna examine that the piping flow channel, the piping risk at each flow channel. Also, we can estimate the core erodibility through that path B and path C. The piping flow path A is a relatively easy problem compared to the path B and path C. Why? Because the embankment backfill material used the pre-screening material showing the relatively uniform gradation, the range. And also dam structures attached, the core structures on downstream area, we employ the filter media to reduce that piping problem. So for the path A, I think the probability of the piping risk is relatively small compared to the path B and path C. So how we can evaluate that path B and path C? Because the alluvial soil strata S1, S2, it shows a wide range of the particle size distribution curve. So very complicated how to evaluate that piping risk for these types of wider variety of particle size distributions available. The first thing start is you need to estimate the erodible particle size. So you just draw that horizontal line, and then that line that encountered each individual particle size distribution of alluvial soil gradation curve. That crossing point, you collect that and gather, and you make that erodible particle size corresponding 20% and 10% of the mass loss. And how you can evaluate that the piping flow channel size? Each individual particle size distribution, you can derive that constriction size curve presented as a green line, and depends on the relative density, and 28% corresponding, you determine that the piping flow channel size. So coarse particle greater than this piping flow channel size will remain. After piping process, this kind of a red dot line will be regradation curve for your particle size distribution over the soil strata after piping problem. And this table summarized the output of the piping flow channel size and associated that the mass fraction related to the fine migration. And you can apply the 9 different particle size distribution curve, and you assume the 2 different scenario, loosely packed condition and the densely compacted condition. So each scenario you can evaluate the piping flow channel size, and also associated that the water fine fraction, particle fraction, mass fraction is eroded out. So you can see the loosely packed condition shows the consistently is a high value of a piping flow channel size and the mass fraction of a erodible soil. And you evaluate that all this collected the data and then mean and the standard deviation for describing that piping flow channel size. So as I mentioned earlier, you evaluate that risk of a piping failure from the compare two data distribution, erodible particle size and piping flow channel size. This is a conclusion table of a probability reliability analysis. So it shows that compare the risk output from the reliability analysis. So you compare the PSD and PSD and 10% of fine particle migration and 20% the piping, the erosion particle mass. It's corresponding, the PSD is a 27%, 11%. And PSD, the piping flow channel, and 10% and 20% the mass fraction loss is predicted as with the probability 13% and 5% respectively. So you can see that compare those 10%, 20% erodibility, and the PSD is a more likely producing the piping problem. And you can also compare the core erodibility through the PSD and PSD, and you can check that mass erosion 20%, 30% of a core material. You can see the PSD shows consistently shows the higher the probability failure, the piping problem risk. So this conclusion, the reliability and probability approach of alluvial foundation soil based on the field lab test data, which is available from your site investigation before the dam construction. And that could evaluate the risk of assessment of piping susceptibility and more objectively. So random and non-uniform feature of alluvial soil showing the wide range of gradation and consolidation degree and could be depicted and compared with the stochastic parameter presented at mean and variance of erodible particle size and also piping flow channel size. And this slide contains a recomposed from 3 published paper presented in Georisk 2017, USSD 2014, ICOR 2013. So if you're interested in reading my published paper, I'm willing to share that paper if you request that through my personal email. I'm still open to joint research opportunity for the model parameters study with the follow-up and the bench scale and field scale and the experimental work. So your lab is fully engaged these types of research, and feel free to contact me for the co-work opportunity. And also you can, if you have any question and comment on this presentation slide and the previous published paper, you can reach me through this my personal email address. And I'm also willing to share my beta version of the Excel program. I briefly showed during my presentation upon your agreement on the non-commercial usage. Okay, and I appreciate your attention, and then from now on I'm gonna receive the questions. Thank you.